Okay. So, good afternoon, students. Today, I'm going to tell you about the gravimetric analysis. So, before I actually start the gravimetric analysis, I would like to give you a brief introduction about the analytical chemistry and its importance. You see, the man is a very greedy person, and therefore, over the centuries during its development, what the man has done, they have manipulated the material around them to best of their use. And to use any matter or material around us that is available, we need to know two things. That this material or matter, what it is made up of. And then when we know qualitatively, and this is what we call as qualitative analysis in chemistry, we know the composition. Then we want to know how much that component or whatever that we want to use is, how much it is. And for that purpose, we have this branch of a chemistry that is being called quantitative analysis. So, analytical chemistry as one branch of the chemistry, and the analytical chemistry has two major branches. One is the qualitative analysis, the other is the quantitative analysis. Now, qualitative analysis you have been doing in your schools also. Thereby you be, say for example, carrying out the qualitative test for the various cations and anions present in a salt or a mixture. Similarly, one can also carry out the analysis for the organic compounds. Now, with regard to the quantitative analysis, majorly two techniques have been employed historically. One is called gravimetric analysis that we'll study today. And the other is volumetric analysis that you will be doing tomorrow in another class, right? So, as far as this gravimetric analysis is concerned, therefore it becomes a tool for a quantitative analysis. And the word in itself, the gravimetric analysis, gravi means weight, metric means measurement. So, weight measurements or the mass measurements or its determination for an analyte. What do you mean by analyte? Something to which we want to know that how much it is. Something, some component which is under investigation, right? So that is being called the analyte. So gravimetric method therefore is analysis which is based on the measurement of mass of a particular component, one component, maybe a combined compound or a mixture that we would like to do. There are two major types of gravimetric methods. Those are being in use. You see, if you go by the first one, that is what you call as the precipitation method. Now, in a precipitation method, the first requirement therefore becomes that the analyte should come into a solution form. And once it is in a solution form, a selective precipitation is done for a component for which we want to carry out the analysis. So therefore, it is called precipitation method, where it is being converted out of a homogeneous solution. A particular compound is being converted into an insoluble form. Now, it is not necessary that the form will be retained. It may not be. Say, for example, if I make a solution of a barium ion. Now, barium ion would be converted by a suitable reagent to an insoluble form, let us say barium sulfate. We all know barium sulfate is highly insoluble in water. So, we convert it into a barium sulfate form, and then it is being filtered off, removed out of that solution, and by finding out how much weight of a barium sulfate has been found, we can determine how much barium was originally present in the solution. So that is a technique that we say for the precipitation method. So obviously there are certain steps involved, which by and large you can say the precipitation is being carried out for a sparingly insoluble compound, and then it is being filtered, washed free of the impurities so that all other impurities are being removed. Only the pure barium sulfate is being there, and then converted into a known. Many a times what happens is that when we are trying to remove water, it may be converted into some other form. This is not true for barium sulfate. Barium sulfate remains barium sulfate even when the heat treatment is done. But say, for example, we are carrying out an estimation for iron. Now, for iron, we precipitate it from the homogeneous solution in a form of the iron hydroxide or hydrated oxide, we preferably call it. Now, when we heat it, hydrated oxide is converted into its anhydrous form, right? Similar, more examples will be taken as we proceed further. But it is being converted into a form whose stoichiometry must be clearly known to us. We must know that after the heat treatment or the drying of a precipitate is being carried out at a fixed temperature, at a given temperature, then what is the ultimate form that as a precipitate we get? And this actually leads to the success of a gravimetric analysis. One, that the compound that we have precipitated should be pure enough. It should not be accompanied with any kind of impurity, because we are going to weigh it as, let us say, barium sulfate or as iron oxide later. Or it has, secondly, to be moisture free, and its formula should be known to us, so that the formula weight later on can be used to back calculate how much iron originally was present in the solution, right? Second is called the volatilization method. Now, in this, the analyte, that means the component which is under investigation, it's being decomposed by heating. So ultimately, say for example, we have begun with calcium carbonate. So we give a heat treatment, it is being ultimately losing carbon dioxide at some temperature and becoming calcium oxide. So ultimately we know something has been pulled out of it and rest is being left. Now here two techniques can be used. One, if we know the left out is a pure component, the left out residue is a pure component, then we can weigh it directly and find out how much calcium oxide is there. So how much originally the calcium carbonate or the initial component was there. Secondly, we can also imply a technique that the carbon dioxide which has been liberated can be trapped in some other way and measured how much carbon dioxide has been liberated out of that component originally. So volatilized product of the decomposition reaction can therefore be trapped and analyzed to back calculate how much original compound was present. So this is what you call as the volatilization method. Next slide, please. Now, this technique, although is very, very old, but even today it has a very big relevance. Big relevance in a sense that the normal analytical tools that we employ today, maybe there are very instrumental, high instrumental method, the advanced instrumental methods are known to us or available, but yet some of the analysis of, let us say, a water sample can be carried out even with this simple technique in a very simple way. Let us say we have taken a water sample from a natural source. Now, you all know that it is never a very clean sort of a water. It is always being contaminated with certain other things. It has some undissolved components, maybe a mud or some other impurities or other pollutants present in a water sample, and some dissolved components. Now, both can be analyzed by use of this simple gravimetric technique. What you have to do is, you take a sample, measure its volume, just filter it. Now, after filtration, whatever the mud or the insoluble component, those are there, undissolved components are there, you can dry them at a fixed temperature. Say in a even air oven, you heat it for at a temperature around 100 degree to get rid of a moisture, and finally you come to know how much undissolved impurities or components were present in a given sample. So this is a way, I mean, by weight actually we have found out. So we can also find out the percentage, how much undissolved component were there. We can say these many, total was the volume of this and total mass of the, let us say the water sample was this, and out of which these were the undissolved ones. So we can find out the percentage. As you had been doing, you have studied about mole concept. So when you know about the mole concept and the percentage formulas, you can always recalculate how much it was. Then out of the dissolved component, after the filtration, the filtrate, I can dry it. I can heat it strongly, a little stronger, and I can evaporate all the water. Then something solid may be left. Those were the components which were there as a dissolved component in the water sample. So I can know even the dissolved solid present in a water sample. So this is all actually becoming nothing but is a part of the gravimetric analysis. Take another example. Here, as I was telling you about the barium and the iron also, we are taking this as an example where silver nitrate and sodium chloride reaction yielding silver chloride and sodium nitrate. It's a very simple reaction and well-known reaction where a highly sparingly insoluble compound, sparingly soluble compound, silver chloride that is being precipitated. We all know this reaction, right? Now, this reaction can be used not only for the analysis of silver, but also for the chloride. In a, let us say, even a water sample, if I want to know how much is the chloride in a given sample, I can treat it with silver nitrate, I can precipitate out silver chloride, and after that, I can just filter it off, wait, dry it, wait, and know how much therefore originally chloride was present. And same is true even if it was a, I wanted to know in a water sample, in a sample, how much silver ions are there, right? So we can use this. Next slide, please. So for any gravimetric analysis, therefore, these three things become important. If we are carrying out a reaction, as we did in the case of a chloride and a silver ion resulting into silver chloride, we must be aware of what sort of chemical reaction or the chemistry of that change is there. We should know the stoichiometry, how many silver ions are reacting with chloride. Say, for example, if barium 1 ion is reacting with sulfate, or maybe in some other case, it is the iron 3 reacting with 3 hydroxide ions, and so on and so forth. So we must be aware of the stoichiometry, and we must know what is the final product. Its composition must be known to us. Unless we know these three things, if we are carrying out a gravimetric analysis by carrying out a reaction, converting into insoluble form, we are not aware of any of the three, will not be able to find out what was the original concentration, right? Okay, next slide. These becomes the steps for any gravimetric analysis. You see, the first is that whatever sample we take, we'll take an example and try to explain these various steps. Let us say we have iron powder. We do not know how much iron it has. It may be having certain impurities which may be insoluble. And we want to know how much iron it contains. So what do? We take, let us say, a gram of the iron powder sample. We weigh, know its exact weight, and then we heat it for a while, say at 100 degrees centigrade, so as to make it dry. So it doesn't have any moisture in it. Other volatile things, if at all is there, they are being removed. Then after that, what do is, we try to bring this sample of iron into its solution form. So what do? We add, let us say, dilute sulfuric acid. The ferrous ions are being formed in form of ferrous sulfate. So once the ferrous sulfate is formed, we can also add some nitric acid to convert it into the ferric ions. Ultimately, all the ferric ions are there. It's a yellow color solution that we obtain. Once we are sure the full iron has been oxidized to iron 3, we can even carry out a test with a very small drop of water. The iron 2's present can be detected with the formation of Persian blue with the ferricyanide reagent. So you can add, taking a drop out of it, of the ferrous solution, And if it gives a blue precipitate with ferricyanide, we know that ferrous ions are still there. And if you do not get a blue color, we are sure that all the iron 2 has been converted into iron 3. So now we are ready with the solution in a form from where we can carry out our estimation, right? Then the third step becomes here the precipitation. Now we have a solution which contains iron 3 and we want to convert it into a precipitate. We know that the iron hydrated oxides or iron hydroxide as you call it, they are highly insoluble in water, right? So what do? We start adding a 1:1 ammonia solution drop by drop to this solution and stir it well. We can take the solution in a very dilute form. I'll come to it a little later that why this gravimetric analysis through this method usually being carried out at dilute form. And then ammonia solution, a precipitating agent is being slowly added and we start getting the hydrated iron oxide as precipitate, red-brown color precipitate starts forming. We have to continue the addition till all the iron 3 has been precipitated as iron. There are methods to check even the completion of the reaction. That means all iron 3 has been converted into iron hydroxide. Then comes a step, digestion. This step is very important. It has its own importance. While discussing the theory of it, I'll come to this also, that why digestion is important. But digestion here simply means, for you to begin with, it simply means that the beaker in which all this reaction, the precipitation has been carried out, we keep it on a water bath for a half an hour, let us say, and try to heat this constantly for some time so that digestion of the precipitates are being done. What is digestion will come a little later, but it is a very useful step. Once the digestion is done, we are through with this step. We see the precipitates of the iron hydroxide, they are being settled and we get a clear solution above. And at that stage, we start the filtration. Now, filtration here can be done in various ways. There are ways by which we can use some ashless filter papers. Those can be employed where this solution is being poured and the precipitates are being removed from the solution, right? Now, that ashless filter paper has a quality that when we burn it later to convert this hydrated iron oxide into the iron oxide anhydrous, then those filter papers while burning do not leave any ash. So what we get is only a pure iron oxide, right? So once this filtration we are through with, or otherwise in some cases, we can also use some specially designed crucibles. Crucible is something in which this heating is being done so as to remove moisture and other things, right? So digestion and filtration, after filtration, we can use some specially designed sintered glass crucibles also for the purpose, depending upon what is the nature of the precipitate. If we have to heat it very strongly, we prefer to use silica crucibles. If we have to heat to a low temperature to get a dried precipitate of the component, then in such a case, even sintered glass crucibles can be employed, right? Thereafter, once this is being filtration has been completed, then we carry out washing. The washing is important because something may get stick to the precipitates. We'll come to it a little later while explaining you what and how we are getting a pure. But washing is to be done because the success of any gravimetric analysis lies that the compound that has been precipitated through this method must be very, very pure. It should not be contaminated with any other impurity salt. Otherwise, when we'll do the final weighing, that salt will also be weighed along with and it will introduce the error. So that is being done, washing is being done. How washing is being done, what are the reagents, what are the various solutions that we can employ, we'll come to it a little later. Finally, as I told you, if it is a G4 sintered glass crucible to a particular temperature, we can heat it. After heating, we get the pure precipitate. Or we can ignite it. Ignition is normally being done in the silica crucible. That means ashless filter paper. It is being burnt at a very high temperature, say somewhere around 1000 degrees centigrade, where the filter paper is burnt out. It is ashless, so it doesn't leave any ash. Only the precipitate is being left in the crucible. And this crucible, whatever we are using, they must be pre-weighed. Their original weight should be known. When there was no precipitate, along with the precipitate, the weight is known. So by taking a difference, you can know how much precipitate has been formed. Now, once you know this, you can back calculate to know how much originally the iron was present. So when you can calculate the how much iron was present, the total compound that you have taken, you can calculate the percentage purity of the sample, right? So this is how we do it, and we get different steps being, I've explained to you a little bit of the steps, those are being involved in the gravimetric analysis. Now we'll go a little further in the experimental details before we come to the calculation part. In the examination, there is a very little question, those are being asked on the steps involved, but more of a question they are being asked on the basis of the calculations which are involved. So we'll come to some of the examples and we'll try to solve them here, right? Okay, next slide, please. Now, there are certain properties of these precipitates which we have to take care. The first is, of course, these precipitates are to be very, very pure. To a maximum, they have to be pure. Otherwise, if they are contaminated, we will not get the correct results. Error would be introduced, as I explained to you earlier. And the precipitation is being done so that the stoichiometry of the compound is also known to us. We can't make a precipitate whose stoichiometry is not always uniform. So we like to precipitate in a form where its stoichiometry is known to us. And we use a reagent that has been called precipitating reagent. That also needs to be very, very selective. Selective in a way, say for example, as I was explaining to you the iron example, if there is some other metal ion, and if that also being precipitated along with iron, once again, the problem of error would be there. I want only iron to be precipitated as iron oxide, and that too full. The reaction should go to almost completion. Reaction should be quite fast. Then only I'm likely to get a correct result. So this is being done. Now, the precipitate that is being formed, we all know when and how the precipitation takes place. When the precipitation takes place out of a solution, when the ionic concentration of the components that exceeds, if it is an ionic salt, ionic concentration exceeds that of a solubility product value, right? So when it is being done, we would like the precipitate to have certain properties. It should be more of a granular or a bigger size particles so that they can be filtered with ease. There should be a minimum formation of a colloid. Colloids are those substances whose particle size is smaller than that of the suspension particle, and therefore they cannot be filtered with ease. And while precipitation, if we do not carry out that precipitation under a suitable condition with use of a suitable knowledge of the chemistry, then what may happen is some colloid may be formed, and that hinders our the filtration process, and also some of the component may even pass through the filter paper or through the G4 sintered glass crucible into the solution, and some component which we wanted to analyze may be lost, and therefore that once again can introduce the error in the gravimetric analysis, right? So it has to be readily filtered, washed free of contamination, sufficiently low solubility they must be having, and so that there is no significant loss of solid that occur during the washing. And during the washing, they should not be very soluble. They should not undergo peptidization with ease, right? And unreactive constituents of the atmosphere. The unreactive with the constituent. Unreactive with the constituent means, say for example, if I have converted into a form which can easily react with atmospheric oxygen to convert it into some other form, maybe partially or fully, and I do not know how much oxidation of that compound has happened in the atmosphere. So it has to be stable. Otherwise, the composition or stoichiometry of the precipitate would be unknown to me, and I cannot therefore back calculate to know how much originally the component or the analyte in which I was interested would be known to me. Okay, next slide, please. So what we have realized here is that when we carry out the gravimetric analysis, the particle size and filtrability of the precipitate is important, right? If it is important, so we want them to be bigger in size, as I was explaining to you, that those can be washed, and ultimately we get precipitate which is pure enough that can be used for the analysis. Next, please. These are the factors which can determine the particle size. What are those? You can have solids form which have varied particle sizes. The precipitates can have a varied particle sizes. One extreme is the colloidal suspension, as I was telling you. The colloidal particles show no tendency to settle, as we know, and form solution, settle from the solution, and nor they are easily filterable. So, for a good gravimetric analysis, therefore, I must set up a conditions whereby I can reduce the possibility of colloidal formation. This I have to take care of. On the other extreme, they are the particles with the dimension of the order of 10th of the millimeter or greater. They are temporarily dispersed, and such particles, they are called crystalline suspensions. Such solutions which have these sort of particles, they are called crystallized suspensions. And the particles of crystalline suspension tend to settle spontaneously, and they are readily filterable. So I would like to reduce colloidal suspension, try to have conditions where colloidal suspensions are not being formed. At the same time, I would like the precipitate to be of a crystalline suspension, in a crystalline suspension form, right? Next slide. Now, these is a very, simplistic sort of a formula. It's a very simplistic thing that we have carried out. That particle size would depend upon the Q and the S factor. You see, here, what is Q? Q is the concentration of a solute. In the beginning, I told you that if you want to carry out a successful gravimetric analysis, you have to start with a dilute solution, not a very highly concentrated solution. So we can have a concentration of a solution becoming important, and S is the equilibrium of solubility. We have studied about equilibrium of solubility, so that is there. Now, if for supersaturation, Q minus S upon S, that is the formula. So I have to control my conditions in a manner so that Q minus S upon S is large. If it is large, then the precipitate would tend to be colloidal. Or I have to control the situation where Q minus S upon S is small, where a crystalline solid is more likely to be formed. So in such a case, therefore, I have to adjust my Q and S in a manner so that the second condition is met, not the first. So what do I do, therefore? Next slide, please. Now you can see from here, there are experimental variables which can control our Q and S values. And if I take a dilute solution, right, and the temperature is being enhanced, the S is being increased, therefore Q minus S would tend to be smaller. In such a case, therefore, I am going to get more of particles which are of a crystalline suspension nature, right? And hence, the gravimetric analysis is being carried out in dilute solutions, number one. Secondly, it is being preheated to a certain temperature where the solubility of undesired components increases and the contaminants become more of a soluble in the water, and only the main precipitate that is being separated out of the solution, right? So this is how we control the particle size. Smaller the rate of the precipitation, more time it takes, bigger will be the size of the particle. Faster the precipitation is carried out, therefore, smaller will be the particles those are being formed. And hence we say you add ammonia solution, let us say in the iron estimation of iron, drop by drop only, so that slowly the precipitates are being formed and we get a bigger size particle. Okay, next slide please. There's one thing more that we said. We are digesting the precipitates. How the digestion will help? Digestion helps in manifold. Digestion dissolves the undesirable precipitates if formed along with the main precipitates. This is one. Because while heating, those impurities will once again go into solution if they have come out of the solution. Secondly, the smaller particles, if at all formed of a main product also, they can redissolve and precipitate again by combining them together into a larger size particles. So by both ways, therefore, the digestion helps. Next slide. We also take care of coagulation of colloidal particles being done if at all some colloidal particles are being formed. So we set up conditions where we add an electrolyte to the sample in which the estimation is being done, so that the colloids are being disturbed, they are being converted into the coagulated form, right? So some electrolyte, we all know, you have studied about these colloids? No, not yet. But when you study about the colloids, you will appreciate that colloids are being stabilized by double layers of a positive and a negative charges. Those come onto the surface of the particles. So those plus and minus charges, whatever the charge that the colloid is being carrying. So what we do is we add another electrolyte that disturbs its double layer stability and convert it into a suspension form. So colloids can be converted into suspension by adding a suitable electrolyte, whereby its colloidal suspension nature changes into a crystalline, not exactly crystalline, but coagulation of colloid, we say, that is being done through this method. Okay, next. This is also interesting. I mean, it is just the reverse of it. You have a suspension. By virtue of certain conditions, experimental condition, you may be getting converted into a colloidal form. And this step we need to control. This normally happens while we are carrying out the washing. At a washing stage, if we do not use a electrolyte that is being dissolved in water as a wash solution, in such a case, what may happen is that through the process of a peptidization, our solid may be converted into a colloid, and then it is being passed through into a filtrate. And hence, while we use a wash solution, the wash solution is usually added with certain kind of electrolyte, which can disturb the process of colloidal formation, and a suspension once again is being retained in the form of suspension. So this process of peptidization has to be reduced. The formation of a colloidal suspension has to be reduced. Peptidization also has to be reduced, so it is not going into the colloidal form. Okay, next slide. This is what exactly I was, say for example, at a digestion at an elevated temperature when we are carrying out. Now you see what is happening. This smaller silver chloride here, and they are once again, because of an elevation in temperature, going into the solution, combining with another silver chloride and forming a slightly bigger particle than later. So smaller particle, as the temperature increases, we know the solubility increases. So the smaller particles, they get dissolved first, they dissolve them and they convert into bigger. The bigger one may again combine to form further bigger ones. So reprecipitation helps through the process of digestion. Some precipitate may be the main precipitate that has been formed. We wanted that precipitate, but its particle size is very, very small. So we have redissolved it. We have again precipitated it. We have redissolved it. We have allowed the smaller particles, in fact, through a process of digestion, to combine together to form the bigger particles. At the same time, on the main precipitates, something may get attached, which is there in the solution in form of ions, or maybe in form of certain kind of a precipitates, which we'll refer it to as a co-precipitants. Co-precipitants means something that has precipitated along with the main precipitate. So that also can be redissolved when we are heating. So undesired precipitates of, let us say, some sodium nitrate that is being, or silver nitrate that is being formed during the reaction, those can be once again forced back into the solution while the process of digestion. Next. This is also showing that how the chloride ion that is being absorbed. This is the layers of chloride ions which are there on the main precipitate, let us say, of a silver chloride. So these chloride ions can be disturbed by adding adequate another electrolyte, so that the process of accumulation takes place. Okay? So this is what you call is the primary absorptive layer of chlorides here on the main lattice, and this is a colloidal AgCl. And when we get counter ions, this stability structure is being destroyed, and hence we get a suspension and not a colloid. Okay, next. आगे चलिए. There are various degrees of contamination in gravimetric analysis, as I was telling you. It is not only the co-precipitation, but also the post-precipitation that takes place. These need to be avoided. If you want to carry out a good gravimetric analysis, the co-precipitation and post-precipitation need to be avoided. What do you mean by co-precipitation? The co-precipitation, they are the soluble impurities, in fact, like the silver nitrate or sodium nitrate in AgCl. We are adding let us say, any sodium chloride with silver nitrate, forming silver chloride, and sodium nitrate is being formed. So there are soluble impurities, soluble things, electrolytes, which are there during the course of this reaction that is happening. So what may happen is, at the coarse particles, which are the main particles, those are being formed, some ions may get attached to them. There are various ways. In fact, there are 4 ways by which these additional ions, which are undesirable for the main precipitate, may get attached to them and can increase their weight. So they are being labeled or termed as co-precipitates. So they are the soluble impurities which comes along with the main precipitate. We want to avoid them. We'll see how to do it. One method we have already seen. Post-precipitation, after the formation of the precipitate, then some soluble impurities may get settled onto them. And this happens after some time, not along with the precipitate main formation, but after the time. So it is called post. Once the main precipitation is completed, then something else get just settled onto it. Okay, next. So co-precipitation, we have seen, is a phenomena in which soluble compounds are removed from the solution during the precipitate formation. They are getting along with them. There are 4 types of co-precipitation. First is the surface absorption. That means silver chloride surface has been formed. Some ions gets absorbed onto it, right? The second is mixed crystal formation. A silver chloride crystal is being formed. There are silver and chlorides being arranged in a peculiar manner in a silver chloride crystal. So some silver ions, they are being replaced by similar size of other cations. If our original solution has some impurity, or maybe even sometimes even the potassium ions or the sodium ions, these ions are there. So they replace them into the crystal as a whole. Now they become very difficult to remove, in fact. So when they are getting just some kind of a, you can say, deformity in the crystal that is being introduced by replacement of the desired cation with a impurity cation out of the solution. This happens when the crystal is being grown. This doesn't happen afterwards. This has to take place when the crystal from a nucleation, it is being developed. Okay. Then there's a accumulation and mechanical entrainment. These are all things which are happening together, and some undesirable, therefore, co-precipitants may get absorbed onto the main, get precipitated along with the main precipitate. Okay, next slide. Surface adsorption, as I told you, the common source of co-precipitation that is likely to cause significant contamination, they can be washed, therefore. We can use a wash solution to wash them. While we say that we are washing the precipitate, it is this type of a co-precipitant that we, if at all they are being left, we are trying to remove them. Okay, next one. This is the minimizing the adsorbed impurities on the colloids. I mean, here also we carry out the initial precipitation in a manner so that no such co-precipitation can occur. You see, we normally say whenever you are precipitating anything out of a solution, you keep stirring, let us say. Why do we say we keep stirring? We want no localized supersaturations to take place. For example, if I have sodium chloride solution and I'm adding to it silver nitrate solution. Now, silver nitrate solution, when added, its concentration where the drop falls in that particular region is very, very high. So, if along with this sodium chloride, the sodium and the nitrate concentration also becomes significantly high, silver chloride may be precipitated, along with that sodium nitrate may also be a little bit precipitated alongside. But if we are stirring it, we are disturbing it, we are not allowing localized supersaturation situation to arise, right? So localized supersaturation can be avoided, and hence we are unlikely to get the sodium nitrate or the co-precipitates to be precipitated along. Similarly, before the precipitation start, what do is we increase the temperature of the solution. We heat it, we increase its temperature. So if at all sodium nitrate is likely to be formed because the temperature is high, so it keeps in a dissolved form. It remains in a solution form than getting precipitated. So increasing the temperature, stirring it, digestion, washing, all these steps are actually helping in removing the co-precipitant in one way or the other, right? So this is what we normally do. Along with this, we will also like to coagulate the precipitate. Okay, next chaliye. Questions with the other thing. Mixed crystal formation. The mixed crystal formation, as I have told you, they are replacing, the cations are replacing, the anions are replacing their original position by some other anions or cations. Now, the extent of mixed crystal contamination increases as the ratio of contaminant to analyte concentration increases. Jitna highly concentrated hoga, you will have to face this problem. And mixed crystal formation is troublesome because little can be done about it. Since in the main crystals, the cations have been replaced by another cation, the anions have been replaced with another anion, we are more or less becoming helpless when this happens. And some error then likely to be introduced in the estimation. Okay. Next one. Sometimes this mechanical entrainment also take place, and when a crystal is growing rapidly, so we have to therefore avoid a rapid growth of a crystal. The process of precipitation should therefore be delayed or slowed down, right? This helps in removing this kind of a co-precipitants. Those are taking place. We have to sometimes also, for the first one also, the initial that the earlier one that we have discussed, we may also have to sometimes change the precipitating agent if the problem of error during the estimation is becoming more, right? So both occlusion and mechanical entrainment are at the minimum when the rate of precipitation formation is low. We have to go there for a slow rate of precipitation for this. Okay, next one. एक मिनट जरूरत बनाइएगा पूरा, हाँ पूरा ही कर दो, पूरा दिखा दे, ठीक है. Okay, now these are the examples. We are trying to estimate barium as barium sulfate. This is the actual reaction that we are interested in. The barium ion was there in the solution. We have added sulfate in maybe in a form of a sodium sulfate or maybe in a form of sulfuric acid we have added to the solution. The barium ions, they are reacting to sulfate and forming insoluble barium sulfate, which can be dried, filtered, dried and weighed to know how much barium was there in the original. Then the contaminants like maybe it may be containing a chromate. So barium chromate is also highly insoluble, so that can be precipitated along. So the contaminants will go and get accumulated inside the crystal lattice of barium sulfate. In the barium sulfate itself, crystal will get some kind of contaminants. This co-precipitation, if not being avoided or minimized, then the results would be erroneous, and digestion of the precipitate and reprecipitation, they are normally being employed to avoid the co-precipitation. Next, Chelly. Next slide, please. These are the examples of the post-precipitation. We are converting calcium into a oxalate form. These are all standard methods that we normally, for the estimation of calcium, we convert it into its oxalate insoluble form and we estimate how much calcium was originally present in the solution. So we normally employ ammonium oxalate for this purpose. Now, if along with the calcium, there is a magnesium present alongside the calcium as an impurity, then magnesium oxalate will be precipitated once the calcium has been precipitated, and it may take a little more time to get formed. So after the main precipitate has been precipitated, formed, we are allowing the solution to be in contact for a larger time with the main precipitate. Such post-precipitation can take place, and therefore what do is we do not, once the precipitation has been, will not like to delay the process, will like it to be filtered off as early as possible after digestion and other things are being completed. We cannot afford to keep it overnight. That will help in post-precipitation of some other components. So to avoid post-precipitation, we have to carry out this estimation once the precipitation has been done and the main precipitate is in contact with the solution, the remaining of the solution. So we'll like them to be separated as early as possible. Okay, next. Then comes the last step, drying and ignition. Once the filtration has been done, we would like it to be moisture free. Only the main component, Bose composition is known, Bose stoichiometry is known to us. We like it to be there. So we have to heat it or ignite it. If the moisture can be removed with ease, say somewhere around 120 degrees centigrade, we can use G4 sintered glass crucible, we can heat it, we can remove moisture. And experimentally, what do is we heat it for a while, let us say for 1 or 2 hours. Then we weigh, again we heat it, try to find out if there is difference in the weight, there was some moisture, therefore it is being removed. We keep heating it and weighing it again and again till we get a almost constant weight. So we are sure now after heating to a particular temperature, there is no more loss of moisture or water taking place to the atmosphere. That can be taken as a weight for the precipitate. Okay. Next. These are the, different types of crucibles. You can show the photographs. These are the different. This is a porcelain crucible. This is a silica crucible. Silica crucible, it can withstand a very high temperature, even up to say very, very high temperature of 1300-1400 degrees. If you heat it, nothing is going to happen. And the precipitate along with the paper, that is ashless paper, can be put into the silica crucible. It can be burned there. The paper will be burnt last. Nothing is left. Only left is the main precipitate. These are the G4 sintered glass crucible by virtue of which carry out the filtration as well as the drying of the precipitate. Both can be accomplished in the sintered glass crucible. It has a more advantage. So at a low temperature, if we can dry the precipitate, main precipitate, we prefer to use sintered glass crucible, provided And this G3, G4, this means the pore size. How much pore size is there in the sintered glass crucible? That those are being there. Next one. So in short, let us now just summarize what we have learned. We have a weight sample which is to be analyzed. That means the analyte. We add some precipitating. We make it a solution of this, that. Then we add precipitating agent. We get the precipitates of the main, and then we heat it. That is what we call is digestion. After digestion, we can filter and dry it. And lastly, we can weigh the sample. So the process of gravimetric analysis, therefore, is that we weigh the amount of precipitate that has ultimately been formed, and we can back calculate to know how much analyte was present. Right? Next one. These are the calculations involved. Next one. You see, one thing what is called is the gravimetric factor. The gravimetric factor is nothing but formula weight of the analyte. Let us say we have begun with barium chloride. And barium chloride is being dissolved to get a barium chloride solution, and then we have added sodium sulfate to it to form barium sulfate as insoluble. So the formula weight of analyte means barium chloride's formula weight. If it is barium ions, then we can use the atomic weight or atomic mass of the barium. Then it is being it is the ratio of the formula weight of analyte to that of formula weight of the precipitate. We have barium chloride's formula weight divided by barium sulfate, right? Into this ratio into moles of analyte to the moles of the precipitate. Moles of analyte to the moles of the precipitate, right? We can also get the gravimetric factor by gram of analyte to the gram of precipitate of the, in grams only, right? We can calculate the percentage analyte. How much percent? The weight of analyte to the weight of the sample into 100. Simple. This is how we use weight by weight composition formula, percentage formula, right? These are the various, formulas. Similarly, percentage weight and analyte means weight of the precipitate into the gravimetric factor and weight sample into 100. If you take it, you will get weight by weight analyte, percentage weight by weight analyte. Okay. You can note it down, this formula, because these are going to be used. Yes, please. Have you noted down? Next slide, please. Okay. Let us find out now, as an example, the gravimetric factor for silver chloride, let us say. So, to know how much the chloride has, the mass of the chloride, the molecular mass of the AgCl, this is the atomic mass of chloride. So this becomes 0.24 becomes the gravimetric factor for chloride in silver chloride. Now, how will you find out the gravimetric factor for silver ions in AgCl? Yes, atomic mass of silver, molecular mass, or the formula mass of the silver chloride. You will get the gravimetric factor for the silver in silver chloride, or barium in barium sulfate. So barium upper molecular mass. Okay. So a gravimetric factor actually nothing but it converts grams of a compound. Now this is important to keep in mind. This factor converts grams of a compound into grams of a single element. Right? Okay. Next one. This is what you have already been knowing, but it is essential to have a recapitulation of this because this scheme of things would be very, very important. You are going to back calculate from some grams, we have to convert into moles. Moles of the another thing is to be find out, and then ultimately the grams of the original compound. So there is some mass of a reactant that we have weighed, dissolved, undergone some kind of a reactions, changes, formed precipitates, filtered, dried, and ultimately the product. So mass of the reactant. Now you can convert the mass of the reactant to the moles of the reactant. Therefore, so divide कर दीजिए. X grams divided by the molecular mass, you will get the moles. Now, out of the moles of a balanced equation, you can use the stoichiometry now to find out the moles of the products. It is not essential the 1 mole will give 1 mole of a product. 1 mole may give 3/2 of a product or whatever. So stoichiometry, the balanced chemical equation is here important. If we know the balanced chemical equation, we can know the moles of the product, though those are being formed in a chemical reaction. And ultimately, through this, the moles, I can find out the mass of the product, how much mass is. So this is a very simple conversion that we usually carry out in any chemical change. If we want to know that if these many grams of the initial substance was there and that has been finally converted into a product, so what is the mass of the final product that is being obtained during a chemical change? And if it is being done in solution, somehow we also have the moles of reactants, its direct relationship with the volume of the reactants. If it is, let us say, 25 ml of a sample has been initially taken, then some gram of any final product has been formed, so we can know what was the molarity initially and so on and so forth, right? So there has to be some thing that you have to, so molarity, moles you can be converted into the molarity if total volume is known, and the volume of the reactant, therefore, it has a relationship with this. Volume of products also has a relationship. So this is a scheme normally that we employ for any chemical change to know initially what was the amount that we have taken of a substance converted into how much it is. Okay, next. This is a sample question for you. Now, knowing these relationships, try to work out through a gravimetric analysis. This is a direct application of gravimetric analysis. We know the experiment, how to do it in general now. So what we are doing is, we have a plaster of Paris, is a white powder that is used to make cast of a supporting broken bones. It consists of calcium sulfate and a little of water, little bit of water. What is the percentage of calcium sulfate in the 0.455 grams of plaster of Paris if reaction with excess barium nitrate produces 0.6168 grams of dry? So you first try to write down the equation. First try to write down the chemical equation. This calcium sulfate, some water is there along with the calcium sulfate. Initially, calcium sulfate was 0.4550 grams, and it is being reacting with barium nitrate. So reaction यहाँ हो जाएगा exchange reaction has taken place, right? This is the situation. when you write the equation, you know this is the situation. Next slide. Now, how do we proceed for this? The mass of the barium sulfate will tell us the moles of the barium sulfate. Once you know the moles of the barium sulfate, you know the moles of the calcium sulfate through this chemical equation. Once you know the moles of the calcium sulfate, then you know the mass of the calcium sulfate. And once you know the mass of the calcium sulfate, you know what is the total weight of the sample that initially we have taken. So I can find out the percentage purity. Right? Please try. Try it further. Now you know the scheme. Mass of the barium sulfate, convert it into the moles of the barium sulfate. How will you convert it? You know it. In that I have given just a slide early. Here I have given the molecular mass, the formula mass of the barium sulfate. Formula weight of the formula mass of the barium, 233.43. This I have given as a dihydrate, 172.172 is the molecular mass of the calcium sulfate. You can note it down this and try to work it out. Have you noted down these two? Okay. Next slide. Now, use this scheme to work out. It's very simple. Although the formula weight of calcium sulfate was not required, I have given it otherwise. That is not required. Barium sulfate's formula weight is required. So, mass of the barium sulfate, you know. Have you calculated the moles of barium sulfate? How will you calculate? 264, something like that. Next slide दिखा दीजिए. Result दिखा देते हैं. You have converted the mass of barium sulfate to the moles, so you will get 2.643 × 10⁻³ moles. You have to only divide it by the molecular mass. Then convert the moles of barium sulfate to the moles of calcium sulfate because they are equal in numbers. Stoichiometry tells us that equal moles would be formed. So same number of moles of the calcium sulfate, we know they are there. Now convert calcium sulfate to the grams, right? So when you convert it into grams, you will get 0.3598. You know how to convert it into mass? Once you know the moles, you can convert it into mass, no problem, right? So once you have converted into the mass, then take the ratio of the two, this and this, multiplied by 100. That will give you the percentage of. This was the mass that you have initially taken of the sample. This is the calcium sulfate that it has, mass of the calcium sulfate that after gravimetric analysis we got it. This is the mass of the sample. So multiplied by 100. यहाँ लिखना शायद इसमें आ नहीं रहा, वो उधर चले गया. अच्छा, इधर चले गया. Multiplied by 100. So we will get it, the percentage of calcium sulfate. This is the simplest example that we can give for the direct use of gravimetric analysis. Direct use of gravimetric analysis. You got it? Okay, next slide, please. We come to another question. It is not that we can only calculate barium or calcium, that means the metal ion. We can also calculate about the chloride or the sulfates. This is one example. Calculate the amount of sulfate as barium sulfate from sodium sulfate. There is a sample of sodium sulfate. We wanted to know how much sulfate it has, right? Now, how do we proceed? The sodium sulfate is treated with a solution of a barium chloride. Now, we are adding barium chloride to it. So, sulfate would be precipitated as barium sulfate. The reaction would be this. Barium ions are coming from barium chloride, sulfate from the sample of a sodium sulfate. They will be forming insoluble barium sulfate, right? Now just see, the molecular weight or the molecular mass of the barium sulfate is 233.42, we have seen. The formula weight for sulfate is 96. The reaction we can write. So in a very similar way, because we are not doing it for any particular amount of sodium sulfate, therefore I have taken it as X, right? So if it is 1 gram, you use substitute X as 1. If it is 1.23 grams, you substitute X as 1.23 gram. In general, I have discussed so that you can use for any amount to calculate. In fact, you will appreciate that this is becoming nothing but gravimetric factor multiplied by the weight of the sample that I have taken, right? Suppose the weight barium sulfate is obtained is X grams, so 233 points, sorry, X I have taken it as a weight of the precipitate of barium sulfate. So gravimetric factor multiplied by X will tell you these many grams of sulfate straight away. So the initial formulas that I have given to you that will be used in the gravimetric analysis, it is a direct use. There we have converted to moles, this, that, right? Now here is an example which can use the gravimetric formula that I told you. Directly you can use it to convert it into grams, right? So gravimetric factor for sulfate in the barium sulfate multiplied by the weight of the precipitate of the barium sulfate that we obtain, right? So we can convert it. Now, if initially the solution was 25 ml, so we can also convert it into how much ultimately the sulfate that we get. This is all total calculations that we can carry out. Because it is the solution of sodium sulfate. So solution can be a given solution. So jitna bhi volume hai uska, you can use that and totally convert it into the X grams of barium sulfate that ultimately being formed. We need not even know if it is 25 ml. Then 25 ml you can calculate it for a liter, or if it is not given, you have to stop here, right? If the volume is given, then you have to go a little further finding out. Right? Next. This I think is almost the same kind of a thing. Calculate amount of zinc oxide from zinc sulfate. Reaction zinc sulfate plus sodium carbonate giving zinc carbonate. Zinc carbonate is ignited. This reaction. This is zinc Zn. Sorry, it is getting cut. So zinc carbonate ultimately, when ignited, forms zinc oxide and carbon dioxide is liberated. Certain metal carbonates, when heated to a particular temperature, they tend to lose carbon dioxide and the oxide is ultimately formed. So when we are trying to, the precipitate of a zinc carbonate is being formed. So when we are trying to remove moisture, they at a high temperature, then they also decompose to result into a new compound. What is more important for us is that we know what has been formed here, right? We may not be able to dry zinc carbonate, but we are able to get a dry product of zinc oxide. So we have converted into zinc oxide, and then from there we are back calculating how much was the amount of zinc oxide from zinc sulfate that we have obtained. A similar kind of example is this. We'll go to a little more tedious examples in the next few slides. Okay, come to the next, because time is limited. This is how we can calculate boric acid from borax. For this, obviously, one need to know the chemistry behind it. Unless you are able to write the chemical reaction, suitable chemical reaction, therefore, whatever inorganic chemistry that you will study about these various compounds, that is normally being hiddenly asked in the examination from you. Unless you know the properties of these compounds which you normally study, which are there in your syllabus, and you know the what reaction, what changes it undergoes. So such questions are becoming little tedious or difficult to solve, because the overall change one need to know, right? Now, once again, this is borax. The borax, when heated strongly, it has been converted into boric acid. Water and sodium chloride is being formed. So, knowing the molecular mass of the borax and the boric acid and the practical yield, let us say in X gram, one can find out how much boric acid is being formed, right? A similar kind of a situation. These type of questions, they are being asked in exam. One need to know the chemistry of it. Next challenge. Please note down this question and try to solve it. Now here the volume of a solution is being mentioned. 25 ml of lead nitrate with an unknown concentration. We do not know how much lead nitrate is there with the unknown. So it becomes an unknown sample. It's a sample with an unknown concentration that is being there. We want to analyze it. Again, once again, it is a direct application of gravimetric analysis. So 25 ml of lead nitrate solution with the unknown concentration react with excess. We have added the rubidium arsenate in excess, Rb3ASO4. After filtering and drying, we get, that means the gravimetric exercise is being done. These many grams of the precipitate is formed. What is the concentration of lead-2 nitrate solution? We want to know the concentration of lead-2 nitrate solution. This solution we want to know the concentration. Okay. The formula weight for the compound that is being formed is given here. So firstly, we should be able to write the chemical equation. Yes. Anybody can write it? Easy hai, not difficult. You have to concentrate that two reactants are given, and in fact, one of the product that is going to be formed is also given. One of the two products. You can complete the reaction looking at them. Are you been able to write it? The equation. नेक्स्ट स्लाइड दिखा दीजिए, टाइम कम है. You see, 3 moles of lead nitrate reacts with 2 moles of this rubidium arsenate, and it forms the lead arsenate plus 6 moles of rubidium nitrate. I have given in 1 step, you can do it in 3 steps. You know, this much of grams of a product, the precipitate that has been formed, so it is being multiplied with the, because it is the 1 mole of the Pb3ASO4 twice. So its formula mass is given. Then it is the 3 moles. So it has to be multiplied by 3 moles. The 1 mole of this, right? So ultimately, and 1 upon this 0.250, because I have converted them into milliliters, I have converted them to liter, 1. So these many moles of lead nitrate per liter. So this becomes the concentration. This becomes the concentration. So it is not that we are always trying to find out the mass of the precipitate or the mass or the composition. We can also find out the composition. If you closely try to examine the first plaster of Paris case, you can find out if this is pure plaster of Paris, then how much is the water? What percentage of water is present in the overall formula? Then you can calculate how much is the water, its mass. If you know how much is the water, then what is the formula of the compound? It will come out to be calcium sulfate dihydrate. We can go on, we have gone further to even know the formula of the initial compound. Similarly here, it is not necessary. I am giving you various types of examples because it is not that simple mass to mole to mole to mass calculation. We can extend it a little bit to our knowledge of the mole concept that we have studied, and we have carried out various questions. The information derived from the gravimetric analysis can be clubbed with our other knowledge so that full numerical example can be solved. So when it comes to the competitive examination, it's not merely the simple conversion type of a question those are being asked. The questions which are being asked, they club the two concepts at least, so that your understanding and linkage between the two concepts is whether clear to you or not. They'll try to check it. Okay. So any doubt about this? It's very simple and straight otherwise, but you have to keep things in mind, right? Next one. In a gravimetric determination of phosphorus, an aqueous solution of dihydrogen phosphate is treated with a mixture of ammonium and magnesium ion to precipitate magnesium ammonium phosphate. The same technique can also be used for the estimation of magnesium. It can be used for the estimation of phosphorus. Okay. This is heated and decomposed to magnesium pyrophosphate. So when we try to remove water out of the precipitate and we heat it to ignite it, we do not get the magnesium ammonium phosphate. Ultimately, that is being converted into magnesium pyrophosphate. Magnesium pyrophosphate is Mg2P2O7. Right? That is being weighed. A solution of this yields 1.054 grams of pyrophosphate. So pyrophosphate that is ultimately formed is 1.054 grams. What weight of sodium hydrogen phosphate was originally present? That we want to know. Right? Here the atomic masses of sodium, hydrogen, phosphorus, oxygen, whatever they are being involved, they are being given to you. This question also appeared in one of the competitive exams. So this is a kind of a level that the questions are being asked. So again, it's a direct, simple application of the gravimetric analysis. But here one needs to know, once again, more important is firstly the chemical reaction that is being involved. If you have been able to write the correct chemical equation, then you can use your mole concept and the gravimetric factors wherever required to convert it or to know how much initially was the analyte present in the solution. Give a try a little bit, or otherwise I will just give you the solution of this. नेक्स्ट स्लाइड दिखा दीजिए, इनको सॉल्यूशन के बारे में बता देते हैं. Here the reaction is that the sodium dihydrogen phosphate reacts with magnesium and ammonium ion to form magnesium ammonium phosphate. That when heated produces magnesium pyrophosphate. Now how we have to go about it? We want to know this initially, how much it is. So we from the reaction know that 1 mole is going to give us the 1 mole of the product. So we write the milliequivalents of sodium hydrogen phosphate is equal to the milliequivalents of the magnesium pyrophosphate. And milliequivalents of sodium hydrogen phosphate is nothing but the weight that was dissolved in solution in 2000 divided by 120 by 2. Why we are dividing by 2 here? This is the formula weight of this. Why we are dividing it by 2? 120 is nothing but the formula weight of this. Why we are dividing it by 2? Anybody can tell me? Because we are dealing in equivalents. So why we are dividing it by 2? Because it has 2 replaceable hydrogens. So its basicity is 2. So when its basicity is 2, so while converting into the equivalent, we have to divide it 120 by 2. So it is the equivalent mass that we can use when we are dealing in milliequivalents, not the molecular mass. Okay. Similarly, milliequivalents of magnesium pyrophosphate is ultimately this much of the precipitate, right precipitate of the magnesium pyrophosphate that we get, W into 1000 milliliter divided by, this is the formula mass of magnesium pyrophosphate. Why divided by 4? Why now? Can you tell me why divided by 4? Because this cations, magnesium 2. So 2 plus 2 plus 4 is the charge on the cation, and P2O7 is also 4 minus. This is P2O7 4 minus. This is the anion. So on cation or anion, both have the plus 4 or the minus 4 charges. Therefore, 222 divided by 4, you can calculate W. You can calculate W. Just do the mathematics, you will get the W. So W, sodium hydrogen phosphate, comes out to be 1.1395 grams. Can we take another example? Okay. Next. Now this is very typical, very typical. I mean, it is a little advanced application of the gravimetric analysis where we are dealing with the mixture. Till now we were dealing with the simple systems. Now we'll try to get something out of, some information for a mixture. A mixture of sodium chloride and an unknown metal chloride. It has been mixed with another, not a metal chloride, but a chloride. that is being mixed. Unknown chloride has been mixed. So there are two observations. Two observations. One is that 1 gram of this, that means the mixture is dissolved in water. Excess of acidified silver nitrate solution is added to it. So chloride, therefore, all the chloride, whether they are coming from sodium chloride or they are coming from the other chloride, they'll all be precipitated as silver chloride. So silver chloride mass that we are getting is 2.567 gram. They are actually, the chlorides are not coming only from sodium chloride, but also from the MCl, right? That is being found. This is observation 1. The second is that 1 gram of the original mixture is heated to 300 degrees. If we heat it, some vapors come out of it. Something gets sublimed. Something gets sublimed, and which are absorbed in silver nitrate. Now what we are doing is the vapors that have been getting sublimed, we have got a silver nitrate solution, we're trying to pass it through it, and the silver nitrate, that vapors there, that is absorbing acidified solution. And some amount of, that is not becoming clear, I'll just try to see it from the slide otherwise. If you will just reduce it, then you will get it. Just slide show से बाहर आ जाएंगे तो पता चल जाएगा कितना है ना. हाँ, 1.341 gram of white precipitate is found. Find the molecular mass of the unknown chloride. The question is this. कट रहा था ना तो उसको थोड़ा उसमें. So we have used two things. One, we have converted all chloride into silver chloride. That means the chloride coming from sodium chloride as well as MCl, that has been converted to silver chloride. In the other case, what we have done is, we have just sublimed something out of the mixture. Now it is a chance that the other chloride was sublimable. Sodium chloride is non-sublimable. So something else that was as a chloride, MCl was sublimable. It sublimed, and when passed through acidified solution of silver nitrate has converted into silver chloride. So here the observation B will tell us about something about the M, right? That means how much chloride we are getting from MCl, at least we'll know from the second observation. From the first, it is the total. So by difference, I can find out, therefore, then how much is the equivalent mass of the M, it can be calculated, and finally the composition. Or I can try to identify the MCl if possible. Okay. Solution दिखाइए जी इसका. Of statement 1, it has, let us say, the mixture has A grams of the sodium chloride and B grams of MCl, but total weight is 1 gram. So A plus B is 1. This we know from statement 1. This means milliequivalents of sodium chloride and milliequivalents of MCl will be equal to the milliequivalents of silver nitrate used in the first case. Right? Because overall reaction is simply this. Chloride combines with silver nitrate, forming silver chloride plus nitrate. The chloride is coming from both the sources, right? So what do we do is, we know milliequivalents of silver chloride. What is the milliequivalents of silver nitrate? Mass of silver chloride that has been precipitated divided by molecular mass of silver chloride is 143.5 formula mass into 1000. So whatever that is coming out to be, this is milliequivalent of both. So we know total milliequivalents of the NaCl plus MCl. Now come to the second. Now, since the mixture is heated at 300 and NaCl is stable, the possibility seems decomposition of MCl, and thus not decomposition, in fact, it is the sublimation. So reacts with silver nitrate. So MCl is now, milliequivalents of MCl will be milliequivalents of silver nitrate consumed in the second step, in the second observation. And I can therefore say 1.341 divided by now 143.5 thousand. These are the milli equivalents of, just to know milli equivalents of sodium chloride, out of the total, subtract MCl's milli equivalent, I get the milli equivalents of sodium chloride, right? कोई डाउट है इसमें यहां तक? सिंपल है, बस इट्स ए क्वेश्चन ऑफ दैट वी आर यूजिंग मल्टी स्टेप and we are trying to analyze a mixture, not a single component. This is an example of analyzing a mixture. Okay. You got it? No problem up to this stage. So milli equivalents of MCl out of the milli equivalents of AgCl, we have found out, and they are coming out to be 9.345. So out of the total, we have subtracted the milli equivalents of MCl to get a milli equivalents of NaCl. Next slide, please. Now, of course, the weight and the molecular mass, formula mass of the sodium chloride into 1000 will be the milli equivalents of NaCl. I can therefore find out how much was the mass of the sodium chloride. So A is being determined. If I know the A, I also know the B. Okay. Now, instead of knowing the B, what I do is that, since I want to know what is the molecular mass of M, since M divided by 1, this is W, M divided by 1. 1 I say because it is only plus, plus charge, chloride. So from this equation, I can substitute this is 0.50 M. So I can find out the molecular mass of the MCl. Molecular mass of the MCl. And it hints that probably MCl was ammonium chloride. Ammonium chloride is sublimable. So it is nothing but, in fact, B divided by M into 1000. That has given us the molecular formula of MCl. Okay? Is that right? One or two more examples we can take. Time is limited. Next one. This you try of your own. Okay, let us take salt example. This you can do it later. You can note it down, and you can try at home. But these sort of questions are also being asked. I mean, what is important here is that I do not know which halide is present here. I can use gravimetry to find out which halide is this, whether it is chloride, bromide, or iodide. So what has been done here is a hydrated salt, a dihydrated salt of barium halide has been taken, where X is a halogen. I do not know which halogen is this. Then it is being converted into barium sulfate by treating it with sulfuric acid. How much I got as a barium sulfate? I have found out what was the initial weight of barium chloride. And from there, I have tried to calculate, recalculate, back calculate what is the atomic mass of X? दिखा दीजिए इसका solution इनको. We know this 233.40. Just atomic masses अगर दिए हों, you can calculate 233.4. You can calculate the number of moles. Number of moles will be the mass of the barium sulfate that has been precipitated divided by the relative molecular mass. So it will be this much. Now we have to apply our mind to find out that what is the original molecular formula, relative molecular formula of the BaX2.2H2O. So from there, we have converted into this because these are the moles, this is the mass that we got. So we have found out the relative molecular mass of the BaX2. Now knowing the atomic mass of the barium, that has been subtracted. So I get the, and the water component 2H2O, I get what is the X2 contribution. The X3 contribution, what is the contribution of X then? X is 35.41. So knowing the X being 35.41, I know it is chloride. If it is bromide, it will be 17. So accordingly, this is an example where it helps through a gravimetry to know which halide is this. This is another example. नेक्स्ट दिखा दीजिए इनको एक एग्जांपल नोट करना है रुक जाओ रुक जाओ I again repeat, I mean what we have done, we have from the molecule we have calculated the number of moles as in the first slide, the scheme of things I have given you. From there we have come to know the relative mass of the BaX2 2H2O. Knowing the number of moles in the mass, we have calculated the relative molecular mass of BaX2, back calculated, and then out of this we have subtracted Ba plus 2H2O. This we have subtracted to know what is X2. Once we know the X2, we have calculated the X. The contribution of X2 in the molecular weight formula, and X ultimately is being calculated and it is being identified as chloride. One more question we'll do and then we'll end our talk. Now, this is an example where we have to determine the amount of magnetite. That is a mixture of Fe2, FeO and Fe2O3 in an impure ore. The purity of the ore is not known. So what do we do is that 1.5419 grams of a sample is dissolved in a concentrated HCl. We have taken an ore, we have dissolved it in HCl, and we have made a solution. Now, giving a mixture of Fe2 and Fe3, we add nitric acid. As I told you in the beginning, that if you have an ore, we can convert it into, or there I have taken example of the iron powder. So iron powder being dissolved in sulfuric acid or HCl forming ferrous ions. Ferrous ions are oxidized to ferric ions by adding nitric acid. Now it is a mixture in itself which is magnetite, so it has ferrous and ferric both. So when we add nitric acid, ferrous is being oxidized to ferric. So all we get is now ferric ions. So we have diluted and added water and precipitated as by adding ammonia solution. Same thing that I explained it to you in the beginning of the talk. Then filtering, rinsing, igniting, ultimately we get these much gram of. So we are interested how much the sample we have taken and how much ultimately the Fe2O3 that is being formed. In between are the steps of the gravimetric analysis, right? So you have to calculate the percentage weight by weight of Fe3O in a sample, how much it was. This was the formula mass for the Fe3O4 divided by the formula mass of the Fe2O3 that is being formed, the precipitate, main precipitate. Since 2 moles of iron is in this, and there are 3 moles of iron in this, so 2 multiplied by 2 by 3, this becomes the gravimetric factor. This then becomes the gravimetric factor for this change. So I can use the gravimetric factor multiplied by the weight of the precipitate to know how much is the originally the Fe3O4 that has been taken. How much is the Fe3O4 that is being present in the sample of the ore. So the Fe3O4, that is the amount, divided by the sample that I have taken, multiplied by 100, will tell me the percentage of the Fe3O4 in the ore sample. So analysis of ore is being done, and there must be other impurities, maybe silica or matrix or whatever that is maybe present along with the ore, that is there. But iron component it has only is in the form of Fe3O4 is 53.44%. Again, it is a direct application of the gravimetric analysis in the practical life, where the percentage purity can be determined. The composition of ore can be determined for the main component. How fruitful it will be to extract the iron out of the iron ore, such analysis can be carried out. In between whatever steps that are being written, that is only the way we have converted into iron 3. The ore that has been converted to Fe3O4, Fe2O3, right? Is that right? So we end our talk here, and I hope it was useful to you. Anything you want to ask about this gravimetric analysis and the questions related, you are welcome. Otherwise, we have covered almost various types of examples which are normally being asked in the examination based upon the calculations that are important for gravimetric analysis, right? Thank you.
6 cards. 10 at each center, I think. Or more than 10. Yes, yes, I'm there. Hello everyone. Today's topic is absolute value. And what is this basically? Write down. Absolute value, or we also say modulus. The same thing. Absolute value or modulus of a real number we'll discuss. And what is this basically? It is defined as this is how modulus of a real number is defined. This is modulus of a number is basically what? This gives you this number's distance from origin. So modulus of any number will give you distance of that number from origin, and you all know that distance can't be negative. Okay, so if you have 2 points, suppose A and B, so you can calculate distance in either of the way. So distance from of this point from this point will be this, and distance of A from B will be A minus B. But we, because of this modulus function, we can say both of these should be same. So this modulus function helps you to define so many things. Like if you don't put this, if you are supposed to find out distance of, just consider the real line. Suppose you are finding distance of from -1 to 0. So the same formula, if you calculate without mod, your answer will be what? 0 minus -1, and then if you don't put mod, then this is incorrect. So modulus function is very helpful in finding distances, such quantities. Okay, so if you put mod, then there is no problem. So mod helps you to find out distance. So you are not bothered like which point you are taking first. Okay, is it okay? So by definition, it is clear that mod A is always greater than equal to 0 for all A and for all A belonging to R. For every real number, this modulus will be always greater than equal to 0. Okay. So now graph. This is basically a function. Modulus is basically, I defined here this as a number of modulus of a number, and this gives you basically distance from origin. Now see it as a function. Okay. Now consider this as a function. This is a function. Everybody knows the definition of a function. This is a function. Can anybody knows the domain of this function? Domain will be what? Domain of this function is R, I can say. R is basically minus infinity to this open interval is R. Range, what will be range? Range will be R plus positive. R plus is basically positive real numbers. This is how this function is defined. Okay. Now if you draw this function, everybody I know that knows the graph. This is the graph. This is the graph. It is here minus x, and at this side it is x. This is the graph of this function. Now you just see this by graph. This is continuous function. One more thing, it is differentiable. It is differentiable, this function. You know how to check? How you will differentiate this function? You know na derivatives? You know derivatives of functions? Can you differentiate this function? You know how to check derivative, like whether this function is differentiable or not? Yes or no? No? This function is defined as, this is the definition, no doubt. Basically, this is completely a different function. So, if I say derivative of x, quickly you will say derivative is 1. If I say derivative of x square, you will say derivative is 2x. But this modulus function, simply you cannot differentiate it in a simple way. So, the method is basically how you calculate its right hand derivative and left hand derivative. Just see how we'll check differentiability. So right hand derivative will be for the points x greater than equal to 0. Okay. Right hand derivative means for such points x greater than equal to 0. We'll check the derivative, and derivative will be what? Derivative of x is here for such values for x greater than equal to 0, function is x. So derivative will be what? 1 only. So derivative in this case is 1, fine. Now check in left hand derivative. For for points x less than 0, derivative is minus 1. So you just see left hand derivative is 1, left hand derivative is minus 1. In continuity, you know, if a function is continuous, then left hand limit should be equal to right hand limit. Same is the case for the derivatives. You haven't done it before, but now you just understand for derivative also. For every function, if you calculate derivative, then in every case, right hand derivative should be equal to left hand derivative. But in this case, especially, you just see right is 1, left hand derivative is minus 1. So this function is not differentiable. In other way, there is no formula. So you have to use this method. So this function is not differentiable. So please keep it in your mind that this function, write down, mod x is continuous. Mod x is not differentiable. Can you tell me at which point this function is creating problem? This function is not differentiable. At which point? This function is not differentiable. At which point? Not at all points this function is creating problem. It is very clear. Just see. At 0, this is the problem. Otherwise, at every point, this function is differentiable. So this function is not, this function is not differentiable at, is it clear to everyone? Now I am telling you, now easily you can tell me for this function. This function is continuous. So it now from the discussion, it is very clear that mod function is always continuous. Whichever function inside it is there in the mod, that function will be continuous, but where it is not differentiable? Minus 1. So this, because point is now, so at x is equal to minus 1, this function is not differentiable. And by graphically also, I didn't tell you, by the same definition you can calculate. Okay? And the definition is basically how you will check in this case. How you will check? First, so you have to define the function first. So function is basically, this function will be x plus 1 for the points where this thing is greater than equal to 0. It is minus for the points no less than 0. This you keep in your mind. It is not that both here also you are putting 0. In that case it is absurd. Okay, so this is the function. Can you draw the graph of this function? This is basically for the points x greater than equal to 1, minus 1, and this is for this. So basically y is equal to x plus 1 line for the points for x greater than equal to minus 1, and y is equal to this line for the points Are you able to draw the graph? What is the graph? How you are calculating? This is simply a line for the points x greater than equal to minus 1. So point is basically this. Show me the graph if you have drawn. Only straight lines you have to draw. At minus 1 value is? At minus 1 value is 0. So this is the point. This is shifting only. And this graph you are getting or not? Is it fine? This type of graph you are getting or not? This is the graph you are getting. Basically, it is shifting only. Origin is shifting. For mod x, this was the graph. For mod of x plus 1, only you have shifted the origin to the point minus 1. So this way also you can draw. Okay. So now you just see this function is continuous. This function is differentiable. No. And how to check by graph? This is the sharp edge na, in the graph. If you have sharp edges in the graph at whichever point, at that point the function will not be differentiable. Is it okay? Fine. So you can write down in your, if you have sharp edges in your graph, then you can say that at those points the function will not be differentiable. So modulus function differentiability you got to know. At which points the function will be continuous and not continuous and not differentiable. Is this clear? This thing. One more thing also you are getting from here, like increasing, decreasing properties. Like for x minus 1, this function is decreasing or increasing? You can see the behavior. This function is decreasing. It is not increasing. From x minus 1 onwards, this function is strictly increasing. For this portion, I am writing here only. So graph shows that this function is strictly increasing. And here it, oh sorry. Here it is strictly decreasing. And in this portion it is strictly oh god, sorry, increasing. So 2-3 things are clear. One more thing you can have, you can know, at this minus 1 by the graph, this is the point of minima, because graph is showing that values are going up. So at minus 1, the function having minimum, and that minimum is how much? 0. Because at x is equal to minus 1 is point of minima. Point of minima, and function value is f of minus 1 is 0. So this is the value. This is the minimum value at which point x is equal to minus 1. So I hope that now you can draw the graph of modulus function. Is it easy? Now you just see how we'll draw this. This is positive always, mod function. Now we'll draw the graph of this function. Consider this. Now easily you can tell me this function is continuous, because this function is continuous. This function is continuous, sum will be continuous. At which points this function is not differentiable? 4 and 1. This function will not be differentiable. Now, will not be differentiable means in the graph you will get sharp edges at these points. And now we'll see, we'll draw the graph and then we'll see. So graph, how we'll read this function now? So here 2 points, 2 splitting points, 1 and 4. Okay, so I'll consider the interval in this way. Okay, I think in a simple way we can. This function definition says this will be x minus 1 for the points. This I can say. This will be this negative of minus of x negative of minus x minus 1 for the points less than 1. This is the definition of this function. This modulus, same way I am writing. No doubt. Now we'll see the summation function behavior. So for the points, I am just dividing the interval for like case 1. You can say case 1 for the points x less than equal to 1. And now for x less than equal to 1, situation will be what? This function value will be what? For x less than equal to 1. Quickly judge from here. This function value I am asking, and I am giving you hints that for values x less than equal to 1, you have to tell me. It will be negative. Is it fine? This will be negative. Now for the same value of this function, because I have to consider both. So value for x less than equal to 1, this function is basically for x less than 4, this is this. So for x less than equal to 1, this will be negative. Okay. So negative of what it becomes? This is okay. So minus 2x plus. This is fine. Now case 2. Sorry, I am considering this less than 1 because for 1 this is the definition. Otherwise it will be wrong. Getting the thing? Because for 1 this is the value. I should consider it less than 1. I have 3 parts of the interval. This is one part, this is second part, this is third part. So this part for x less than 1, this is the value. If you are including x1, then in that case this is the value. So it will be a little confusing. So to make this confusion, to not make confusion, what I am taking is x less than 1. Is it okay? Because for x less than 1, this is clear that this will be the value, and x for x less than 4, this is the value. Now I am considering which interval? This interval. Is it fine? Again I am taking less than 4 because equal to 4, for x equal to 4, this is the value. Then again will be a confusion. This is how we make intervals. For this, now can you tell me what will be the value of the function? For this, for x, because x is lying between 1 and 4. So for x greater than equal to 1, this is the value of the function. And now tell me for x less than 4, in this case, this is the value. So there is no confusion. Is this okay? Value of the function. So what is this basically? This is 3 only. This is 3 only. Now quickly calculate for the interval. I am rubbing this now. I think case 3 we can write here. For case x greater than 4. And x values x less than 1 we also write in this way also, na? Meaning is same. In this way also I can write x less than 1, either this or this. There is no difference. For x greater than 4 or x basically lying in which interval? 4 to infinity. Quickly calculate what is the function. Is this you are getting? In this case, you are getting 2x minus 5. Now can you draw? Easy. This is straight line. This is straight line. This is simply 3. So in this interval, value is 3. How you will draw this line? For the case x less than 1. This is basically how you draw straight lines. X and y. For x0, value will be 5. For y0, minus 2.5. So now draw. So for x less than 1, and the next point is for less than 1, this 0, 5 point is 0, 5 and x is minus is this point okay? Just check this one. Plus or minus? It's plus? Plus now. So 2.5 will be somewhere 2, 3. At 1 the value is, at 1 the value of the function is, between this interval 1 to 4 the function value is 3. Is this okay? You know what's wrong here? You know, anybody? Not able to judge? Yes, x should be less than 1 and we have taken value x 2.5. So graph will not come in this here. The line will be till x less than 1 portion. So please keep such points in your mind. Is this okay, this line? And for between the interval 1 to 4, the value is 3. So how many things now you can know from your graph? If this function is continuous, differentiable, not differentiable, because here you are getting sharp edge. Here also you are getting sharp edge. This is the point x1 and this is x4. So at 2 points the function is not differentiable. Okay? Not differentiable at x is equal to 1 and 4. Point of minima, because function values are like after here it is uniform, In this interval 1 to 4, it is uniform 3. So function value 3 at such points in this interval, at each point is point of minima. Each point in this interval. Not a single point, many points between the interval 1 to 4. And the value is at each point 3. Is it okay? So minimum value of the function is 3 in the interval Is it okay? Yes, I'll check. So now you people can draw the graph of modulus function. You can see the and here now also in this portion it is decreasing. Here it is uniform, neither increasing nor decreasing. Okay, here there is no like function is not increasing, decreasing. But after this the function is increasing and point of minima also. Okay. So this is done now. Quick, everybody knows how, graph of sin x. Draw in your copies. Graph of sin x. Function sin x. This time your function is this. Graph of sin x is how you draw. This is trigonometry function. Everybody has drawn. What is the graph? At 0, at angle 0, value is 0. At pi by 2, value is? At pi by 2, sin pi by 2 is? 1. At pi, value is 0. And you know that this so this is the graph. At 2 pi also it will be 0. At this value it will be minus 1. And you 2-3 things I want to know. I want to tell you this function period is 2 pi. Period means that after within the interval period means that after 2 pi within the like 0 to 2 pi, this is the graph, and function period of this function is 2 pi. It means after that this graph will repeat itself. So no need to know the values, just simply the same graph you draw in the 2 pi to 4 pi interval, and the same in the this side, same this side. Is it okay? Period means that values will repeat. The values between 0 to 2 pi, and after that values will repeat. So same graph you will get. And you know also the graph of this function at like different angles, you know the value of the value of sine function. So simply also you can draw. So this function is periodic and period is continuous also. This function is differentiable. Why this function is differentiable? Now by graph, like you have strong proof that in graph there are no sharp edges. Otherwise, for the differentiability, you have to calculate the right derivative and left derivative to give the strong reason. Okay, so by like by seeing the graph, you can say this function is differentiable. There are no points where the function is not differentiable. This is okay. Now for the mod function, you know this will be all the values will be greater than equal to 0. So how the graph will look? One thing you are observing that mod function graph is not coming in this region because values are positive na. So graph is above this x-axis. So in sine case also these values won't occur. Won't occur. So what will happen? This thing will go like, because when you will put this is basically 3 pi by 2. At 3 pi by 2, when you will calculate this value, this will be -1 and mod of minus will be 1. So basically mod sin x function will be like this. Is it fine, everyone? Every value will become positive. So no negative value you will get. So this portion automatically will come here. And for the negative side also, this will be the graph. Now I'm drawing this graph nicely. Is this okay? This graph of mod sin x? So graph will look like this. This is pi value, this is 2 pi, then 3 pi. Here it is minus pi. And this value is 1 minus 2 pi. Is it fine, graph? Okay. Sin x function is continuous, sin x function is continuous, mod sin x function is differentiable. She is saying no. Sharp edges. No sharp edge you are getting? Mod sin x function, I am writing now because you people are judging. I don't know how you are judging. This is the definition. This is the definition. Now, at which points this function is not differentiable, where the value will differ, right hand derivative and left hand derivative. Any idea? Just check quickly. Points are very clear actually by graph also. At x is equal to pi, if I am checking. So at x less than pi, x greater than pi. If you will take any value x less than pi, what will be the function? If you are taking x pi, this value is, I think this way you cannot check. I think we'll do it this part further later on because this way you cannot check it. It is really confusing. So just leave this question. We'll discuss a bit later. So this function is continuous. For the differentiability, how to check the points? From the graph also it is very clear. These are the points. Okay, sharp edges. But now, and this is the graph. For the differentiability, keep it this right now. We'll discuss. Now the graph of this function. Because clearly not a like easy method we are getting. Now sin mod x graph. Mod x, everybody knows. This is the graph. This is the definition. So basically, this function is okay. Now, and sine of minus x is minus x. Now draw. For x greater than equal to 0, sin x graph, simply sin x graph, and sin x graph looks like this. This is the graph. Now for x less than 0, these points, minus sin x, how what values you will get? At 0, 0, for this value pi minus pi by 2 you consider. For minus pi by 2 value will be, please answer carefully. For minus pi by 2, if you will put here minus pi by 2, minus of minus 1 will be 1. Yes, positive. So this will be the graph. At pi it will be 0, no doubt. At minus pi, now it will go like this. So there is a difference. There is a difference in the graph. Sine mod x graph, mod sine x and sine x graph, 3 graphs you have seen, and you can, I think, observe what are the differences. Is it okay? This function differentiability you can check. At 0 only, this function is not differentiable, otherwise it is differentiable. Point of maxima, sin x lie between minus 1 and, so you know the max value and min value of this function. That sin x graph can't go above 1 and can't go below minus 1. Is it okay? I think modulus function. Any questions? Any questions? Now next thing we'll do, properties basically of this modulus function. Okay, one more thing I want to discuss, like in complex numbers. In real numbers, I said that modulus is basically a distance of that point, whichever number modulus we are calculating from origin. But in complex numbers, you know, if suppose this is the complex number, z is equal to x plus iota y, then you calculate mod of z as, this is basically, you can write it in this way. So here also mod is giving you this point, xy point distance from origin. But like complex numbers are like in 2D, x and y, two variables you have. So here the difference mod you calculate in this form. But this is also distance. Here also it is mod function is giving you distance and from which point? Origin. In 2D also, two-dimensional, if you have suppose 2 points, in that case also, if you are suppose this is x point and this is y point, so if you are supposed to find out this is basically what? x1 minus x2 whole square. Is this okay? Here the point is origin. Here this distance is giving you x and y distance. Distance of x from y. Formula is same. So modulus in complex numbers in 2D and in 3D also gives you basically distance, and distance can't be negative. So this property, non-negativity property always holds. Okay, whether it is in complex numbers, whether it is in 2D, two-dimensional geometry, and in real numbers. Is it okay? So this is, and graph also in complex numbers. I won't discuss in complex numbers. Now write down some of the properties, very important properties of this function. Okay, side one more thing I want to discuss for this function. You know even functions and odd functions? You don't know? Okay, I'm just learn the definition only then. Even function, actually this function is even function. Even function's definition is if you change this variable now and you get the same function. Like if this is the function, x square I'll say. This is the function. If you want to check whether this function is even or not, so what you have to do, you just replace x by minus x in the function, and if you get the same function, then you will say this function is even. Okay, so now you can check in our case mod function, this value is always true. So f of a is basically, if you call it f of a, So this function is, so f is equal to mod a, modulus function this negative you will get. F of x will be, when you will substitute instead of x minus x in the function equation, you will get fx is equal to minus f of minus x. In this case, the function odd function property, odd function definition you can say. Is this okay? This is example of even function, that is also example of even function. This is example of odd function. Is this odd function? This is odd function because f of x, f of minus x will be minus x, and that is equal to minus of fx. This is odd function. Now no discussion. I think modulus function, so many properties, so many things we have discussed. Now write down the properties. And with the help of properties, basically we solve it. It helps in solving questions, including modulus. Properties. Number one property is mod a is always greater than equal to 0 for all a in R. This is very true. No need to check. Mod a will be equal to 0 if and only if a is 0. It will, if modulus of any number is 0, then a will be 0. Otherwise, it will not hold. Next is this. This is also everybody knows. Number 4. Mod a is basically maximum of a minus a. Next is product multiplication. So if you have in product two numbers, then separately also you can take the modulus, and both things are same. Modulus of the product or separately modulus of the numbers. Next is in division also it holds, but one condition we need for this, because b is coming in, for b, because this is in denominator, so this should be non-zero number. Now next is this is number 7, and number 8 property. This is important one. This is triangle inequality. And why we call it triangle inequality? Because in like if you are drawing a triangle, in like what conditions you can draw a triangle? Like if you have three sides, what should be the condition? This is the condition. Sum of two sides is greater than the third side. So this property we call as, is it okay? Why we are calling it triangle? Because sum of two sides is greater than or equal to. So this is triangle inequality. Next one is number 9. And AB are what? All these properties holds for all the real numbers. AB are real numbers. Now okay, this is also important for the problems. you will use very often this property. Two more properties. This is also important one. If b is greater than 0, if and only if I'm just telling you why this is so. Rest of the properties for any real number, for any two real numbers, you can check, you can verify. Very simple to verify. Okay. So now why this is so? I rub the rest of the properties. And you just learn, because straightforward, if you will use in your in solving problems, it will take less time. If you will solve the full question, then it will take time. Okay, so using the properties, you can simple your calculation. So the last property is this. The definition of this is mod A is basically A, not mod B, mod A. So it means for A greater, for the case 1, for A greater than 0, this is A only, and condition is basically this. So this becomes A, this is less than equal to B. Is it okay? For case 2, for the points A less than 0, this is minus A. So when you multiply the inequality by minus sign, inequality changes. So this will become, so finally answer is this answer you are getting. This is what I have written. So you can solve also. But I think if you will learn, then I think it is fine. Is it okay how we are getting this? Now for this second part, mod A is greater than equal to B. So mod A, for the case, same case, two cases we are having. For this case, value is A. This is the solution. Okay, for case 2, this is the solution. Is this fine? So in this case, these two answers. Or okay, now signum function, you know, definition of signum function. Anybody? You know or not? Answer? Yes or no? Ooh! Oh my god. Signum function definition, you know, because now I will tell you that relation between how both the functions are related, signum function and modulus function. You know, signum function definition. Relationship between modulus function and we write it as sin x also, signum function. This is the notation. So basically signum function is mod x upon, this is the definition, Now, what is this basically? Mod x is for x greater than 0. Now I'll take this cases, I'm taking the cases separately. For x greater than 0, this value will be x. So x upon x will be 1. For x 0, this value will be 0. This is also 0. So 0 by 0, 0 by 0 is not 0. Okay. Please, we'll discuss this case later on. X less than 0 is minus x. Minus x upon x is minus 1. Now because you people don't know indeterminate form,
नहीं जाएगा नहीं जाएगा कहीं नहीं जाएगा
so this is the signum function. Now I'm stopping this modulus part here. And now I'm starting with, I think for modulus, so many things you got to know. Now I'm starting with logarithms. Okay? Because we have very less time. All of you know that 2 to the power 5 is how much? 32. Everybody knows that. This is very simple to calculate. Now in the form of log. Log is basically a number. It is basically a number. Log of any number. So logarithm is this is basically a number. In terms of log, how you write this? This is basically a base, and this number in log form, this is in log form, you can write this this relation as this. Is it okay? So what's the importance now? Like for a very difficult, I think, calculations, suppose you are asked to find out this. You have done so many questions. If I ask you what will be this value, you cannot calculate. But with the help of log, you can calculate easy. We have log table. With the help of that, you can calculate. So log is very important function. What is basically what function is this? Now just see. Inverses, you know, inverse of a function, you know, all of you, you know how to calculate also. So first write down a definition. Let A is a positive number other than 1 and a to the power m is x, then we say m is called the log of x to the base a, written as log a x. So please, this is very important. A is a positive number other than 1. So this definition is saying if you have this relation and this A is not equal to 1 and A is greater than 0, like I am saying here positive number. Is this correct or this correct? Like positive number I am saying, so A is greater than or equal to 0 or A is greater than 0? 0 is positive or negative? It is neither positive nor negative. So if I am saying positive, so it is not 0 is included. Is it okay? So it is basically A greater than 0. In log form, this is the base and this power will come here and this will go here. This is how we write log expression of this type of exponential function. Now you just see this term, you know, each of you know. What is this now? This is basically, this is a function. This is basically inverse of this function. This function inverse is this. So log is nothing. You reading it, I think since which class? 7th, 6th. You know that how to multiply to three times, 4 times and all. So basically you know this, and after this comes, and this is basically inverse of this function. So inverse of how it has come. You know how to calculate inverse? You know? So I'm calculating, because suppose this is the function. Suppose this is the function. Inverse of this function we want. Suppose nobody knows how to calculate inverse. Nobody knows. So this is the function inverse. Let inverse I'm calculating. Let inverse function is, suppose this is the inverse. Wait. If fx is the function, inverse will be this. This you want. I am letting this function as y, because I want answer of f inverse x, and this I am letting it at y. Now finally I want answer of y. Okay. Now put this value. F inverse x is equal to y implies fx is y. So fx is what? A to the power? No. Sorry. So fx will be, x will be fy. X will be fy implies x is equal to ay. In log form, if you are asked to write, then this is base, this power will come here. Is this okay? So y is what? Inverse. So inverse of this function is this. So log is basically inverse of this number, this function. Is it okay? Log. This is a number, and how it has come? Inverse of this function is this. Aida? So you now, I hope, know how to calculate, how to get the inverse function answer. You can calculate easily. Can you tell me fx is equal to x square inverse? Fx is equal to x square inverse of this, because this is really simple. You should know. X square function inverse. Anybody got the answer? It is
Log base x, log base 2,
log base 2
x equals to
equals to this you got. Really?
then log base x, x
You just suppose that this is this. Okay, inverse function is some y. Then fx becomes, oh sorry, x becomes, x is equal to, this implies x is equal to fy. So x is equal to y square. So y is what? What you are writing, I don't know, like how you got this inverse function. This is the inverse. It's not that I'm teaching log, so every function inverse will be in log terms. I just asked you a simple question. The inverse is under root x. So what value you were telling me? I think you were writing it in this way. Something, I think this is the power, this will go here. This, I think you something, this is how you were writing now. So why you are getting? Why to separately, like this is the inverse, no? Separately you are getting. No need to write y in that form. In last case, what I was getting, x is equal to a to the power. This I was getting. And in this case, value of y is in power. So I wrote it in log terms to know to get y value. But here no need to write now. Simply y you are getting. Is it okay? So it's not every function inverse will come in log terms. So now log function is basically 2-3 things I want to tell you. Graph of this function is, suppose your function is this fx. Okay, log function domain is this. Log is always defined for the values x greater than 0. Log is always defined for the values x greater than 0. It means log of a negative number can't be calculated. Is it okay? You can calculate log of this where this x is greater than 0. Is this okay? Log of negative quantity, negative number you cannot calculate till the date. Is it fine? So now log 1 I will tell you, log 1 is 0. Log 0 I will tell you, if I'm not writing base here, base can be like here I'm not writing anything. I'm telling you the value only. If it is not written, it means base is, because we are familiar with decimal numbers. This is decimal. So this base is, if it is not written, it is 10. So just write down these two values, very important values. Log 1 is 0, log 0 is minus infinity. Log of negative number cannot be defined. Write down. Okay, 1, 2, this function I give you. We got inverse of this function. Inverse of a function is calculated only when the function is 1, 1 and onto. 1, 1 onto functions you know. No need to know then. Because I just want to discuss it thoroughly so that nothing left. Is this okay? Log 1, 0. Now come to the graph. Log, if you are substituting 1 here, x is equal to 1. What value you are getting? 0. So 1, 0. This is x-intercept. X-intercept is 1 0. Okay. Now this graph of this function is this. Log 0 is how much? Minus infinity. It won't touch this line. It will go like near to this line, parallel you can say, till minus infinity, but it won't touch. And now here you have log table. You can see, for different values, you can find out the value and you can see the graph will look like this. Is it okay? This is increasing function. Graph is increasing. This function is increasing. Unbounded also. This function, there are no bounds. Like I draw this graph I drawn. This was also unbounded. Can you tell me any bounded graph? We did in the class only. This is unbounded. Any bounded graph, any bounded function? This is unbounded function basically. Yes, sin x is bounded because values of sin x function lies between -1 and 1. Y is equal to x is also unbounded function. No bounds, na. You cannot bound the value of the function. Here also no fx has no boundation, no bounds. It is increasing. It is not. It is unbounded function. Is it fine? Now write down. Okay, if I asked you log x domain is, domain first we'll discuss. Log x domain is 0 to infinity. Now first we'll discuss domain and range. Suppose this is the function. Base is how much? 3 is the base, greater than 1. Now if I ask you domain of this function, range I didn't write. Range is minus infinity to infinity. Can you tell me domain of this function? Whichever number is here, it should be greater than 0. Otherwise you cannot define. So it means x should be greater than 4. So domain is 4. The range is same, minus infinity to infinity. Is it okay? So log this number should be positive. Then only you can define log. Otherwise you cannot. So it's easy to find out domain of any log function. Domain of this function, can you tell me? Answer carefully. Don't be in hurry. Just think and then answer. Log x plus 7. Anybody got the answer? Any problems? This is really very simple. Fx is log x plus 7. Only you have to check domain, like domain, how you calculate domain? Like I don't know, like how you people are calculating. How you calculate? Values of x, na, where this function is defined. Values of x where this function is defined. So only log x you have 7, there is no problem. There is no x here. So this part is creating no problem. This part will not give you domain. Consider this first part only log x, and log x is log x domain is this. So for this function, domain will be what? X greater than 0, 0 to infinity. So why you people took so much time? Now tell me domain of this function. So domain is basically x greater than 0, 0 to infinity. Points greater than 0. Quickly come to this question. Log base is 5 and 1 plus x upon 1 minus x you have this time. So calculate domain of this function. This should be greater than 0. Then 2 points you have in this case, minus 1 and I know how you have calculated. How you calculated, na? Then only I'll be able to know na that what you did. You multiplied it, na? But this way you don't you don't multiply, because this full expression, if you will remove this x, na, this term, then you cannot come to a right answer. What you are doing, you are multiplying this by 0 and you are removing this term. But to know the domain, this term is also very important. You can't remove. It is not an equation. You are finding where the values of x where this function is defined. So don't remove this part. This is also important. In calculation, you need this. You are removing this, now you are taking it to this side and you are making it 0. So it means that you now for your domain, these points you have removed. So this is not correct. Is it okay? So here 2 points, minus 1 and 1. So 3 intervals. 3 intervals basically. I'll check the intervals in which this value will be greater than 0. And that will be the domain of this function. Is it okay? So for x less than minus 1, tell me. This will be any number you take. X less than minus 1, like minus 2 you can take. Minus 2 will give you what? Negative value or positive value? Positive, negative, quickly come to a conclusion. Minus 2 you are substituting minus and then plus. Negative you are getting? Negative confirmed. Any number you can substitute, any number, and that number should be less than minus 1. Answer will be same. It's not that for minus 2, minus 3 answer will differ. It will be uniform. So x less than minus 1, it is negative. You are getting? So I don't, this will not come in domain, this portion, this interval, these values you can say. Now check in this, minus 1, 2. At minus 1, this value is what? At minus 1. At minus 1. Because I haven't checked at the point minus 1. Na? So check at minus 1, 0 upon 2, 0. So I don't need this also, because I want the values for which this value is greater than 0. So minus 1 will not come in our domain. So now minus 1 less than x less than 1. So now check at x equal to 1 also. At 1 it will be 0 and this will be, so it is infinite number, not defined number. So this will also not come in our domain. Now see this in this interval, 0 is lying in this interval. I can check at 0 the behavior. So 0, 0 positive, 1 greater than 0. So this is this is part of domain of my function, this function. Now this will come because function is positive in this interval. Now for the values x greater than 1, what is the answer? For x greater than 1, 2 you can substitute, negative you are getting. So domain is how much? This is the domain. Is it okay? Please don't do such like mistakes, because you want your calculation is basically on x and you were removing x. So in this way you can't get the right answer. Is it okay? I think now easily you can answer this question. Fastly do it. Domain of this function. So now you can calculate domain of any log function easily. Got the answer? Domain is? This should be Minus infinity to open or close? At 1 it has problem, this function. What is the problem in at 1? Log 0 is minus infinity, so not defined at 0. Is it okay? Now we'll do graph. How to draw graph of log function. Any problems in domain and range? You know graph of this function? Draw the graph of this function. And in terms of log, you can write it as how you are drawing. This is increasing function or not, because for to draw a graph draw graph you need increasing decreasing behavior also. How you are drawing this function? By taking values. You can easily draw. At 0 value is, when x is, this is x, this is y. At x is equal to 0 value is 1, so 0 1, and then this way it will go. You can draw. See, 2 to the power x, 3 to the power x, 4 to the power x. This way you can draw. Now graph of this function. At x is equal to 1, this value is 0. Now you see both the graphs. This is this function's inverse is this, and you see the graphs also. So like it is reflection, na? Reflection. Inverses. Is it okay? So easily now you can draw any log function, na? Easily what you have to do, like if I ask you to draw this this x plus 3, what you will do, you will see where it is 0. It will be 0 at x is equal to minus 3. At that point only it will cut the x-axis, nowhere else, and then simply this will be the, because at x is equal to, this is 0. I just rub this. So at minus 3, this is minus infinity. At minus 3 log 0 is minus infinity. Minus 3 this time, okay. So minus 1, minus 2, minus 3, and rest of the values where this will have where this will cut the x-axis or y-axis. This is the point. At x is equal to minus 3, this value is,
At 0.
this value is 0, but log 0 is minus infinity, where it will be 1. At x is equal to minus 4, this will be log 1, and log 1 will be 0. That is the intercept. Getting the thing? At x is equal to minus 3, this value, this will be 0, and log 0 is minus infinity. It means at minus 3 na, this value is somewhere like minus infinity. You cannot draw. I want the value where this is intersecting x-axis or y-axis. If you take this point, because log 1 is 0, this is the value from where I can get like where it is cutting the x-axis. So at x is equal to -4, this value will be 1 and log 1 will be, okay, wait. Domain of this is this. So it is at -2, sorry, domain is x is equal to greater than equal to greater or this is the domain. So you can't take x is equal to -4 because negative of log you cannot define. Sorry, x is greater than -3 at x is equal to -2. This value will be log 1, 0. Okay, so -2 is this. X is -2 and here it is 0. So graph will look like, and it is going to -infinity. Is this fine? Drawing the graph, it is increasing. Log function is increasing. So this way you can easily draw the graphs. Domain, now some properties. Is this okay? Graph, domain, range. Now write down the properties. Log x is continuous function. Log x is, quickly you should answer. Log x is continuous because you have seen the graph. Log x is differentiable function. Sure? There is no point where log function is not differentiable. Now a derivative of log x is, everybody knows? This is basically x greater than 0, x not equal to 1. I hope now you people will keep it in your mind. This you have to take it. Just cram it. Now properties. Some of the properties you know very well. If you have product here, then you separate it by sum in this way. If you have in division the numbers, then you get this. I am taking base here A. I am taking base A here. Any doubts? If your base and this number is same, then always you will get 1. And this is also very important because in solving problems now, if you have like 1 and you are giving some and you have this type of problem, suppose I'm giving you little bit hint, then like you can't add log in this, then what you will do, you will take advantage of this property. So you can change this one as log AA because base is A na, so I'll take A. Now you can, this is in addition, now you can multiply. So these properties help in solving the problems. Is this okay? This base, if base is same and suppose like, okay, I think I should discuss it later. Log A1 is how much? 0. Next property, number 5th. This also you know, if you have something in power, power comes in front. This Is this okay? Log AX is basically log X upon log A. This is also star. Helps in solving problems. If you have a to the power log base is also a x, then you because if you have some number now and you want to write that number in this form, then with the help of this property you can write. Like if you have 2 here and you want to write 2 in terms of log and base should be 7. Okay, I'm just giving you a hint. You want to write 2 in the form of log with base 7. So how you will write? 7 to the power log 7. Is it okay? I'm just giving you a hint through these properties, how you like in your problems, how you will use, how you will get the help. Is this okay? Suppose base like 2, I write in this form. I'm writing it again. This is 2. If base is 10, you want to write 2 with base 10, then what will be the log expression? Base, I want base 10. Then what should be the number here? This is the hint. No, 2 should be the answer, no? This is base. This is the number. Quickly answer. This is the base. This number goes where? If you are writing in log form. Just think now. This is the base. This is the number. To get y, what we do? We just, this is the base 10. This is the number. How you will get y? 10 square. Getting the thing? If you want to write 2 and in terms of log with base 10. So this is the method now. Base I am giving you, number also I am giving you. I want the number with this number. I want this number. 100. Is it okay now? So like base can be anything, but now I think you people can write 2 in any form. If I am giving you base 3 and number same 2, can you tell me what will be the this? Who said 27? Is this okay or not? Your calculation should be fast, na? So this is how we are getting. Base I am taking anything. So you can write 2 accordingly in any way. Like if in your problem you have 2 also and some other function with base 3. So you can convert 2 with in this form easily. Is this okay? So this property is very helpful. Next is, this is number 7. 8. This is also very helpful. Just see. Log a base a x, log of this number with base a will be in this form. 1 upon base will change and this base will become number now. Is it okay? This property is also very helpful. Next is 9th property. This everybody knows. If base is same, log of 2 numbers is same, is given that this is same, then both the numbers will be same. So this will imply x is equal to y. Is it okay? Now number 10th property. Write down 4 properties, very important properties. This side everybody has written? I am not rubbing. Please write and then I'll tell you. Very important properties. This write down only. I'll explain after writing the 4 properties. Everybody has written. So what these properties are saying, this is your base, and in starting I took A as, sorry, is this okay? Now if your base is greater than 1 and this number is also greater than 1, in this case this property is saying that the log value of this number will be greater than 0. Is it okay? Here in this property it is saying if your A base is lying between 0 and 1, if base is lying between 0 and 1 and your number is also lying between 0 and 1, so in that case also this value will be, and like in what problems these properties help. Suppose this is, I have one question, I'm writing rough. Suppose you are asked to show this. I don't know this number, I don't know this number. So how I'll get to know na that whether if I know this number exact value, then I can compare. Otherwise I can't compare. So here base is greater than 1. In this it is not lying. Here it is not lying. Here also it is lying. Is it okay? 10. Which property like I'll use? This is not, this I can't apply, this also, this also. So by this property, it is true that this number is positive and this number is positive. So when I'll solve this, you will see how we are using these properties. Is it okay? Because like if you are in many problems you just use. So is this okay if your number, if your base is lying between 0 and 1 and your number is also the number whose log you are calculating, that number is also lying between 0 and 1, you will say that this value will be greater than 0. It can't be 0. Here in this case, A is lying between 0 and 1, number is greater than 1. In that case also your value of log will be greater than 0. But in the case where your number whose log you are finding and base is greater than 1, in that case only your log value will be less than 0. Is it okay? So like this is case when A is greater than 1, yani suppose 10, it is greater than 1, and well this value is, in this case it will be, and you all, I think all of you know how to calculate. If I ask you to calculate this value, how you write this function? First you take this point here, by log table you calculate this value like this, na? So first your characteristic will be 1 bar, and then you will see 50, value of 50 at 0. This is how you see log table, na? Is it okay or not? Not? Anybody has problem? You have problem in calculation? Log values? Okay. These properties are okay? How these properties are true, na? Suppose this is log of 5 you want to know. Okay, log of 5 you want to know. The first thing is that you just first number you keep as it is. You put a point after a number. If suppose this is the number, so basically to calculate log, what you do, you just put keep this decimal na here after a number. So how you take this to at this position, it is here, no doubt. So easily you can calculate a log of this number. But here in this case, this point is here, and to calculate log value of this number, I want this point here. So how I'll take it here? How I'll take it here? Only one digit, only one move I'm giving it. Only one move, not two moves, only one move, na? This way I can take it here. So 1 point. Suppose this is the number. You never calculated log. Okay, suppose this is the number. This time your point is here. I want point here. So how many moves? 1, 2. So the value of this 2 point, and then what you will do, you just see the log table and you will find 37. Value of 37 are 4 and 5. This is how you see the log table. Is it okay? So this portion is called characteristic and this portion is called mantissa. Is it fine? If you don't know how to calculate log, then it is really very difficult if you don't know. So this way, then 30, 23. This point I have taken here. Only one move I gave. So 1 point value of 23 at 4 and then at 5. Add करते हैं. Mean जो table में you can see. Then you add and then you write the value here. And to calculate log of any number, you need 4 digits. Is it okay? I can tell you, like, I don't have log table, otherwise I would have told you. So we'll discuss it later. If you are not like good in calculating log of numbers, is it okay? I'll tell you. So is this okay? And if base is not given, base is not written, what base you will take? 10. Okay. So this property is okay. If your number base is greater than 1 and your number is lying between 0 and 1, then in that case log of that number will be less than 0. Is it okay? All the properties. Now this question, it is actually a good question. Suppose this is the question. This you are asked to prove. How you will prove it now? Here base is 7, here base is 11. No comparison at all. Now, no property you can apply directly. So how you will see? Basically, solution. This question is basically you just let this number, this negation, you just suppose this minus this. Consider this. So basically what do you want? If this number is greater than this you are asked to prove. I'm taking this minus this. So this subtraction should be greater than 0. This I want. Basically this I want. But here the problem is this is 7. This is 11. How I make this base same? Otherwise I can't add. I can't apply any log property. So what is basically the method is, consider can I write it like this? I have made base 7. how it is. Which property I used? One property, a number is sixth number, you can see. I have written log 11 13 as log 7 13, log 7 11. I have made base now 7. Is that property okay? So that property says log ax is log x upon log a. So basically my problem was here, I want to make it 7. So to make it 7, I divided by log 7, and then I wrote log 13 upon log 7 as, I can write in that this way. Is it okay? Base I have made same. So you also can make the base same in this way by using this property. Now next is, it means that this number should be greater than 0. This number should be greater than 0. Now multiply. Basically I want this. Now you just see how I'll remove the terms. How I make my calculation simple. Is this number greater than 0? Is this number greater than 0? So to get this fraction greater than 0, only now I want this greater than 0. This I can remove. Is this okay? By the property, this number is positive. It means this number is greater than 0. So I don't need this to show that this is greater than 0. So now I'll consider this portion only. I'll see whether this is greater than 0 or not. Is it okay? So now consider this portion. Consider, okay, I should not cross it. This is greater than 0. So consider log 710, log 711, now you just see what I'm doing. I have divided by 7 and I have multiplied by 7. How it will help? This is now product. So log of AB is log A plus log B. This term. I am just simplifying. And how this trick will help, you just see. Minus is this okay? Log of AB is log A plus log B. Log of 7 is how much? Log of 7 in the base and number is also 7. This will be how much? 1. Is this okay? So basically, I am getting this. Now what I'll do to make my calculation simple, I'll consider this as A, this as B, this as C. So now A plus 1 minus, so multiply and finally you are getting this. Okay. Now you just see how from here how we'll move. This number A is positive. Is it greater than 0 or less than 0? Greater than 0. This is B is also greater than 0. So this number is greater than 0. If anyhow, if I am able to prove that this number is greater than 0, then sum will be greater than 0. So now I can remove this term also, because this I know that this is greater than 0. Only left to show is that this number is greater than 0. So now I am considering this portion only. Is it okay? So now consider A plus B minus C. So it is log 10 by 7, base is 7 plus log 7. Can you calculate this? Log A plus log B minus log C. Which property you will use? You should not see copies. You are very much aware of this property. This will be in product and this will be in division. In denominator it will come. So 10 into is this okay? So finally you are getting 110 upon with base. This number is greater than 0 or not, because this is the conclusion. With the property, this is greater than 0. So finally you got, I started from a subtraction, one number minus second number, and I got that subtraction is greater than 0. So it means that number is greater than the second number. Is it okay? So how we use properties? Is it okay? So this is how you do manipulation to get your answer. So this is, I stop. Okay. Thank you very much. Okay, log values.